this video, we're going to cover section 10, alcohols, aromatic compounds, aldehydes, and ketones. And the material that we cover in this section can be found in the text in chapters 12, 17, and 19. Specifically, we're going to cover 10.1, which will look at the nomenclature of these four families of compounds. Now, before we get into the nomenclature of these compounds, I want to highlight one aspect of this section that we'll be covering in more detail. And that is that we're going to be looking at reactions that allow us to oxidize alcohols to the carbonyl-containing compounds, such as aldehydes, ketones, as well as carboxylic acids. And similarly, we're going to look at ways in which we can efficiently and selectively reduce these carbonyl-containing compounds back to their respective alcohol. And again, we're using these terms reduction to imply that we're forming more bonds to carbon with atoms that are less electronegative. And that generally, as I've mentioned previously, involves the formation of new carbon-hydrogen bonds. Whereas oxidation is the opposite of that. That generally involves the formation of new bonds to carbon that are more electronegative than that of, let's say, a hydrogen atom. So forming new bonds to oxygen is a typical example from which the name is derived. Now, alcohols are compounds that possess the hydroxyl group, that OH group. And so when naming the parent, we replace the E in the parent with OL. So the suffix goes from E, we drop the E, we add OL. And so you can see in this example, we have a 2-carbon system, that's ethane. One of the hydrogens is now replaced with that hydroxyl group, and so we refer to this as ethanol. Now there's no need to include a locant to indicate the placement or position of this hydroxyl group, and that's because it's redundant, and this is typical of small molecules. So it would be incorrect to refer to this as 1-ethanol, simply because we couldn't draw a 2-ethanol. And so in that respect, the locant is redundant. Now that changes if we were to go to a 3-carbon system. For a 3-carbon system, we could draw this particular alcohol as well as this particular alcohol. The first one, this is 2-propanol, whereas the one below is 1-propanol. So in this example, with the propanols, you do need to indicate the locant because you need to unambiguously assign a name that will give you a particular structure. And so we need the locant in that particular scenario. Now for ring systems, when the hydroxyl group is the only substituent on the ring, we would refer to this as cyclopentanol. And when the hydroxyl group is the highest priority group around the ring, it never needs to be given a particular locant because it's always assumed to be carbon 1. So every other substituent with respect to that hydroxyl group on the ring will be given a numerical locant. So for example, if I was to include a ethyl group at that position, we would refer to this as a 2-ethyl cyclopentanol. Now when numbering the parent chain of an alcohol, we give the hydroxyl group the lowest possible locant. And that's despite the presence of alkyl groups or even pi bonds. Halogens the same. So in this particular example, you can see that we have a 7-carbon parent. So that's our hept. We do have an alkene as a part of that parent, so that'll be included as a suffix, heptene. And we do have the hydroxyl group. And so this will be named as an alcohol, so it'll be a heptenol. Now let's look at how we would name this. We have 1, 2, 3 methyl groups, and they're at the 5, 5, and 6 position. So we have a 5, 5, comma 6 hyphen trimethyl hept 6 hyphen ene hyphen 2 all. So this is one way in which you could name this compound using the IUPAC systematic approach. Now you have a little bit of leeway with respect to the locand 6 in this name. You could refer to this structure as a 5,5,6 trimethyl 6-heptene 2-all. But what I've done is I've included the locand just before the suffix for which it represents. So carbon 6 is the first carbon of the alkene, and so I place it before the letters En to represent the alkene functional group. And you can see that we've placed the locand 2 just before the suffix Ol to represent where the hydroxyl group is located on that parent chain. So as we just mentioned, that locand that represents the position of the hydroxyl group, it can be placed before the parent or before the suffix Ol. Both are acceptable, but as you know, my preference is generally to include the locand just before the suffix, so it's very clear as to what the locand is referring to. For cyclic alcohols, as we just mentioned, that bear that hydroxyl group, there is no need to indicate the position of the hydroxyl group as it is understood to be at carbon 1. So everything else with respect to that carbon will be numbered accordingly. So in our current example here, we see we have 2 methyl groups that are 1, 2, 3 carbons away. And again, we want to give those methyl groups the lowest possible locands. If we were to number in a clockwise manner, 1, 2, 3, 4 would be the numerical locand. So the counterclockwise direction around the ring gives you a lower set of locands. So that will be the correct locands to use in this name. And as you can see, we have some stereochemistry, we have some three-dimensionality associated with carbon 1 in this particular example. There are 4 different groups, technically, according to our RS system, attached to this chirality center. And so, as shown, the configuration for this particular structure is the R enantiomer. Now, as you may recall from alkyl halides, we can also classify alcohols based on the number of R groups or alkyl groups that are attached to the alpha carbon of a alcohol. So the alpha carbon, again, is going to be the carbon directly attached, bound to, through a covalent bond, to the hydroxyl group, to that oxygen. And so if there is a single R group attached to the alpha carbon, we refer to this as a primary system. And you'll recall the notation that we used to represent primary was this 1 superscript degree. Similarly, if there's 2 R groups attached to the alpha carbon, we refer to this as a secondary system. And finally, our tertiary alcohol, there would be 3 alkyl groups attached to that alpha carbon. And so we'll be classifying the reactivity of alcohols based somewhat on whether or not they are primary, secondary, or tertiary. Similar to what we saw for the alkyl halides, that the reactivity of the alkyl halides did depend somewhat on the substrate, whether or not we had a primary, secondary, or tertiary system. Now let's look at aromatic compounds. And in this course, we're only going to be looking at the nomenclature of aromatic compounds. We won't be spending any time looking at their reactivity. Now, an aromatic compound is a compound that exhibits conjugated pi bonds enclosed within a ring system. And the most common member of the aromatic family is that of benzene. So aromatic compounds include benzene and various derivatives of benzene. So we will see for many of the benzene derivatives, we have common names associated with them. So methylbenzene is shown here. This is commonly known as toluene. And this dimethylbenzene, where there are two methyl groups neighboring one another, we often refer to this as orthoxylene. Now, monosubstituted derivatives of benzene, these are named systematically, where benzene is the parent, and we list the substituent attached to benzene, or substituents, as the prefix. So in this example, we have a chloro group attached to the ring system, and so we would refer to this compound as chlorobenzene. And again, because there's only a single substituent, we would not provide a locant for that chlorine atom. Because there's only one group attached to the ring system, we would simply refer to this as chlorobenzene. Because we couldn't have a monosubstituted benzene, a chlorobenzene, with a locant other than one. Similarly, we have this NO2 group. This is referred to as the nitro group, and so this structure would be referred to as nitrobenzene. And then if we had an alkyl group attached to that ring system, we would simply use the same nomenclature for alkyl groups, and in this case, we would have ethylbenzene. As we saw on the first slide for aromatic compounds, there are a variety of common names associated with monosubstituted benzenes. And so here's a list of 8 common names that we typically use for benzene derivatives. And so you are responsible for these particular common names. Now, when we're naming benzene systems that contain alkyl chains, we have to be careful about whether or not we treat benzene as the parent or not. So it all depends on the number of carbons in the parent system. And so for a ring system like benzene, that number is 6. And so if the substituent attached to benzene has greater than 6 carbons, a continuous chain of 6 carbons, then we would treat the alkyl group as the parent. It would be an alkane, and benzene in that particular instance would be referred to as a substituent, and we call it a phenyl group. And you've seen me use the notation pH to represent that phenyl group previously. So if we look at this particular example, we have 1, 2, 3, 4, 5, 6, 7 carbons in our chain, whereas there's only 6 in the ring. So in this particular instance, we would treat this as the parent, heptane, and at the 2 position, we would have the ring system, and we refer to benzene as a substituent, refer to it as a phenyl group. So it'd be 2-phenylheptane. Now, if the number of carbons in that alkane are equal to or less than the number of carbons in the ring, so again, benzene has 6 carbons in the ring, this particular chain 1, 2, 3, 4, 5, 6 has an equal number of carbons, but we give precedence to benzene if there's an equal number of carbons. And this is the same rule we applied to alkyl substituted cycloalkanes or cycloalkyl alkanes. It really depends on the number of carbons in the parent. And when they're equal, the ring system takes precedence as the parent. So you can see that we would refer to this now as a complex substituent, where we have this is carbon 1, 1, 2, 3, 4, 5 will be the longest continuous chain of carbons, and at the carbon 1 we have a branch to give us a methyl, so it would be a 1-methyl pentyl. That would be placed in brackets to represent that it's a complex alkyl substituent, and we would then use the parent benzene. And again, we don't need to indicate where this group is attached on the ring because it's the only group attached to the ring. So it'd be redundant and incorrect, actually, to place a 1 in front of this name. Now, the other aspect of naming benzene derivatives that we should discuss is that if you have unsaturation, meaning if you have a pi system, alkene or alkyne, if that occurs in what appears to be a substituent, in those situations, that's not the substituent, but that's given precedence as the parent. So in this particular example, we wouldn't refer to this as a alkenyl benzene of some sort. We would refer to this as butene being the parent, and the phenyl ring would be a substituent. So in this particular instance, we see we have a 2-phenyl, 2-butene, and we must include the stereodescriptor Z to indicate these two groups are on the same side. These are the highest priority groups. These would be on the same side of that double bond. Now, di-substituted derivatives of benzene, they can be named in one of two ways. And so on this slide, what you're seeing here are some benzene derivatives in which they are the parent. And so as you can see in this example, we have a anisole. Here we have a toluene. And here we have benzaldehyde or benzene carbaldehyde. Now, we can refer to the other substituent highlighted in red in one of two ways. We can use numerical locants, in which we would assume in each case that the substituent of the parent would be placed at carbon 1 on that ring system. So every other substituent would be with respect to that particular position. So in the first example, this would be at the 2 position, the bromine atom, the bromo group at the 3, and the chloro group at the 4. And so as you can see what's drawn here, we have a 2-nitroanisole, a 3-bromotoluene, or a 4-chlorobenzaldehyde, or benzene carbaldehyde. Now we can also use descriptors known as ortho, meta, para, and they describe this relationship between a second substituent somewhere in the ring with respect to the substituent of the parent. So a 1-2 relationship is described by the term ortho. A 1-3 relationship is described by the term meta, and a 1-4 relationship is described by the term para. So it's correct to use either the descriptors ortho, meta, para, or to simply use the locant. Either is fine. Now, when naming an aromatic ring like benzene that bears 3 or more substituents, then we can't use those same descriptors. We can't use ortho, meta, para. They only relate to di-substituted systems. So when identifying the parent, it is acceptable and common practice to choose the common name first. So you identify the common name before identifying the substituents. So in this example, we have phenol as our parent benzene derivative, and we have 2 substituents. We have a chloro group and a bromo group. We will alphabetize those substituents, so the B in bromo precedes the C in chloro, and then we provide locants to the relative location with respect to this carbon atom. Now we would have 2 options here. We could refer to it as a 5-bromo 2-chloro or a 3-bromo 6-chloro. And the way to decide is you want to give the lowest possible locant to your set. And so the 2 with respect to chloro is lower than the 3 with respect to bromo. Now let's switch to aldehydes and ketones. And what's similar about aldehydes and ketones is they both contain the carbonyl group, the carbon double bond oxygen. And the only difference between an aldehyde and a ketone is the nature of the substitution to the carbon of the carbonyl. So when there are 2 R groups to either side of that carbonyl carbon, we refer to that as a ketone, whereas if we have 1 R group and a hydrogen attached to that carbonyl, we refer to that as an aldehyde. In addition, aldehydes and ketones are responsible for many of the flavors and odors that we experience in our daily living. And so if you're heading down to your local cafe for a nice fall latte, there's a good chance you're going to have some cinnamaldehyde or benzaldehyde mixed in with your drink. So let's look at aldehydes first. So when naming the parent, replace the suffix E with AL, and this will indicate the presence of this functional group. Also note that because this functional group will always be at the end of a parent chain, we will always assign the first carbon of an aldehyde to that carbonyl carbon. So if we're naming a structure as an aldehyde, carbon 1 will always be this position. And so any other substituent off that parent, whether it's a double bond, a halogen, a hydroxyl group, that will all be with respect to that carbon. So that's explained in this particular example in more detail. So when numbering the parent chain of the aldehydic carbon is assigned number 1, and despite the presence of any other substituent that we've looked at to date. So and that includes the hydroxyl group. So you can see in this example that this will be carbon 1, and everything else will be given a locant with respect to its position. Now, like we saw for ring systems, it's not necessary to include that locant in the name because it's always understood to be the first carbon in that parent system. Now, when we're discussing cyclic compounds, we're never going to have that aldehyde functional group within the ring. It's always going to be a substituent off the ring or attached to the ring. So in this example, you can see I was using the term benzaldehyde and benzene carbaldehyde equally. And you can see in this example that if you have a ring system other than benzene, we can name it in a similar fashion, that we simply name the ring to which this group is bound to. And the term that we use is carbaldehyde. So here you have a 6-membered ring, no conjugation, no pi bonds. It's a cyclohexane ring. We refer to this as cyclohexane, all one word, no spaces, carbaldehyde. So cyclohexane carbaldehyde. If this were a 4-membered ring like cyclobutane, it would simply be cyclobutane carbaldehyde. And of course, for the benzene derivative, you can refer to this, if we were to throw in pi bonds into this structure, well then it wouldn't be cyclohexane any longer, it would be benzene carbaldehyde. Or, as it's commonly known, benzaldehyde, which is a shortened version of this particular name. Now, when we're naming ketones, we're going to replace that suffix E with ONE to represent the presence of that ketone. And unlike aldehydes, the ketone group can occur at different positions within a parent system. It won't be at the end, because if it were there, if that carbonyl group was at the end of this structure, then we would have butanol. And so we don't need to include the location of that ketone functionality in this particular structure because we can't have anything other than that carbonyl at the 2 position. So 2-butanone, that 2 would be redundant because we can't have a 1 or a 3 or a 4 for that matter. But if we were to go to, let's say, a 5-carbon parent, we could have a 3-pentanone, or we could also refer to this as pentan 3-one. We could also have, though, the same 5-carbon system, but we could have that carbonyl at position 2. So we could have a pentane or tan-2-one. So here you see you have constitutional isomers for the ketone when you have a carbon chain that's greater than 4. So typically for small organic molecules, when you're naming derivatives, be cautious of the use of locants. In most cases, they're irrelevant or redundant because you can't draw any other structure that would give you a different locant. So when it's unambiguous, meaning there's no other way you could provide a locant to describe that structure, then it's unnecessary. But when you get to a situation like in the pentanones that you could have 2 possible ketones with a 5-carbon parent, then it's important to include the locant so that you can differentiate between these 2 ketone structures. And similar to what we saw for aldehydes, when we're numbering that parent chain, we're going to give the ketone group the lowest possible locant, despite the presence of any alkyl groups, halo groups, pi bonds, or hydroxyl groups. And so long as the ketone group is given the lowest possible locant, then that will set the numbering for the parent, and then you can use locants to describe the position of any other groups or pi bonds. So we've covered a lot of naming in this particular video. So if you have any questions about the naming of alcohols, aromatic compounds, aldehydes, or ketones, by all means reach out to me with an email. Thank you.